Yeah, so okay. So sort of the goal for the talk today is this is too thick. Um so sorry. Yeah. The goal for the talk today is if we're given an algebra A, then we want to construct and study derived autoequivalences of A. And the motivation for this is just because, well, so autoequivalences of, sorry, the derived category of A, so of this guy. Okay. And our motivation for this is just that autoequivalences of this category are pretty flexible objects which still constrain some properties of the algebra. So, for example, they constrain properties of the stability manifold. They constrain some numerical invariants. And they have something to do with mirror symmetry as well. So, really, also the other motivation for this is that we can apply this to geometry, which is something I'll maybe explain at the end of the talk. Okay, so that's our main motivation for studying these derived autoequivalences. And I wanted to start talking a little bit about a motivating example. So let's say that we have a ring S, which is the quotient of the completed polynomial ring in four variables. Um, by the equation AB minus CD, something like that. Then we can define an S module M, which is going to be given by the direct sum of S and the ideal AC. Then we can define two algebras that we're interested in. First of all, we can define this algebra A, which is going to be the endomorphism algebra of M over S. And we can define B to be the stable endomorphism algebra of M over S. And by this, I mean that B is going to be a quotient of A by an ideal, which we're going to write brackets proj A and or proj S. And this ideal here is what we're going to call so this ideal here is just the ideal of A consisting of maps from M to M, which factor through a projective S module. Okay, so we're interested in looking at these two algebras, and actually we can present them as quivers. So we can present A as the path algebra of the following quiver. So we'll have two vertices, one that kind of corresponds to S, the other corresponds to the ideal AC, and then we'll have two arrows going each way. And this arrow sort of corresponds to A. This arrow here corresponds to C. This arrow corresponds to the inclusion map, and this arrow will correspond to the map D over A. So this is our algebra A in this example presented as a quiver, and we can obtain B as a quiver from A by first deleting the vertex corresponding to S. And then deleting all maps that factor through this vertex. So in this case, we're going to take this quiver and we're going to delete this vertex here corresponding to S and all of the maps that go into and out of S. So all that we're left with is this quiver Q, which is just one vertex and no arrows. So that kind of tells us that as an algebra, B is isomorphic to just the complex numbers, because we're working over C. Okay. So this is our motivating example, and in this example, Donovan and Weems showed that this functor here, so we'll call it curly T, and it's going to be R hum over A of the ideal proj S blank, and this is going to be an endofunctor of the derived category of A. So they show that this functor here is an autoequivalence. And they called it the non-commutative twist. And then maybe before I move on, I just want to have a quick note that actually Donovan and Weems prove this more generally. They prove that this functor T is an autoequivalence. Anytime the ring S is something called a CDV singularity. But we won't need to worry about this in this talk because we're only using this as an example. Okay. So the key idea that we want to take away from this example is that we have a ring surjection E between the algebras A and the quotient algebra B, and this induces an autoequivalence T, which is the arham of A of the kernel of P. Because this kernel of P is exactly the ideal proj S in the example. So the question we're going to address today if we're given a ring surjection from A to B, then when is this functor curly T an equivalence? And the answer is that we're able to specify conditions in two settings. The first setting is that of Gorenstein orders. And the second setting is going to be the setting of Frobenius exact categories. And so this is what I'm going to spend most of the talk talking about. But before we go into that, into the results in these settings, I want to talk a little bit about some of the background that we'll need, which is called twists around functors. So the authors, Ano and Lavinenko, they introduced the concept of a twist around a functor exactly to study autoequivalences of triangulated categories. So let's start with a definition. So following Ano and Lavinenko, let's say that we have a functor S between triangulated categories. A and B. Okay. And then technically, in the background, we should be assuming that A and B admit something called the Morita enhancement. And S descends from something called a quasi-functor. But this is going to be true for all of the functors that we'll consider in this talk today. So although this is in the background, we don't really have to worry about it so much. Okay. So we have this functor S between triangulated categories, and let's assume S has a right and a left adjoint. And let's call them L and R. Okay, so this is our setup, and we can finally define what a twist around S is. The twist around S is a functor T, and this twist is going to be an endofunctor of A, which sits in a functorial triangle that looks like this. Okay, so this map here, epsilon r, this is going to be the co-unit of the adjunction between S and its right adjoint. And I'm saying that, so somehow we're assuming that triangles between functors exist, which is a complicated assumption, and it's why we need to assume all of the DG enhancement assumptions in the background. But for the purpose of this talk, we can just kind of assume that this triangle will exist, and we can specify this functor t up to isomorphism uniquely. Okay. And then also this functor t comes paired with something called the cotwist. This cotwist is the functor c, which is an endofunctor of, oh, sorry, wait. Sorry. So the twist should be an endofunctor of b because we're taking a triangle of endofunctors of b here, right? Okay. So yeah, so the twist is an endofunctor of b, and then the cotwist is going to be an endofunctor of a, which is the domain category of S. Okay. So the twist comes paired with the cotwist, which is the functor that sits in the functorial triangle. And now what we do is we take the unit of the adjunction and then take the cone of that. So this eta r here is our unit of the adjunction between S and its right adjoint. Okay. So these are the definitions of twist and cotwist around functors, and what's really interesting about this formalism and these definitions is that properties of the twist and the cotwist are very closely related. So we can often deduce properties of the twist by knowing properties of the cotwist. And one of the examples of when this happens is this theorem here by Addington and Ano and Lovnienko. Which states that if the cotwist is an autoequivalence, and if we know that the right and left adjoints are related by C, so what I mean by this is that I want the right adjoint to be functorially isomorphic to a shift of the composition of the cotwist with the left adjoint. So if these two conditions hold, then the twist is an equivalence. And this is what we're going to use in this talk. So we're going to deduce that our functor is an equivalence by knowing that the cotwist is an autoequivalence, as we'll see soon. Okay. So for us today, the functor that we're interested in, so we're given a ring surjection A to B, then this induces the restriction of scalars functor. F equals which is the derived tensor over B of B as an A, seen as a BA bimodule. So this is going to be a functor from the derived category of B to the derived category of A. And this is the functor that we're interested in, and we want to compute the twist around this functor. So we've got this functor, and it satisfies the assumptions of S in the definition of the twist. So in particular, F has a right and a left adjoint given by the following functors. So here we have F, and then F has left adjoint, which we'll call FL, and that's just tensoring, taking the derived tensor over A of B, seen as an AB bimodule. And it also has a right adjoint given by R-hom over A of B. Okay, so, and we're going to call this FR. Okay, so the question that we want to answer is, what is the twist around this functor F? And that's our first result for this, for the talk. So the short exact sequence given by, induced by our ring morphism P, well, this induces a commutative diagram that looks like this. And we can construct natural isomorphisms between these two triangles. So yeah, so since the vertical isomorphisms are natural, then the twist T is isomorphic to this functor curly T, which we've defined to be R-hom A of the kernel of our ring surjection. So basically, what we've shown is that if we have a ring surjection P, then we can consider the restriction of scalars functor F, and it turns out that the twist around this functor F is exactly the functor T that we want to study. Okay, and now we're going to use this to prove that in a few settings, this functor is an equivalence. So let's talk about the Gorenstein order setting. Okay, so we'll start with a ring surjection between R algebras, A and B. And we're going to assume that this ring R is a Noetherian local Gorenstein ring of finite curl dimension. And let's say that this finite curl dimension is D. These assumptions here, they're what I like to call geometric assumptions Because in the examples and settings of that we consider in geometry, these are naturally satisfied. Okay, and then what we're going to do is we're going to place an assumption on A. We're going to assume that A is a Gorenstein order. And what do I mean by Gorenstein order? Well, I mean that I want there to be an A bimodule isomorphism between A and its derived dual over R. And then we're also going to place some assumptions on B. So first of all, we want B to be finite dimensional over C. Second of all, we're going to ask for B to have finite projective dimension over A. So if we regard B as an A module, it has finite projective dimension. And then finally, we're going to assume that B satisfies one of two assumptions. So either we're going to assume that it's self-injective, or we're going to assume that it has finite global dimension. Okay, so I like to think of this assumption on B here as a type of smoothness assumption. And I like to think of these assumptions on B here as a type of spherical assumption. Okay. So yeah, so these are the assumptions that we're going to have, and this is our setup. And as before, this ring surjection from A to B induces the restriction of scalars functor. F, and the twist around F is this functor curly T that we want to characterize as an equivalence. So the first result in this setting states that if B satisfies a certain X vanishing condition, so we're going to ask that xk from B to B vanishes for all k different than 0 in the dimension of R, then actually we can compute what the cotwist is, and the cotwist turns out to be a shift of the Nakayama functor of B. So this curly functor n is the derived Nakayama autoequivalence of the algebra B. So, or in other words, of the derived category of B. Okay, so in particular, this tells us that C is an equivalence. So by what I mean by curly C is the cotwist. So the cotwist around F is this functor here, which is a shift of the Nakayama autoequivalence. Okay, so we know that the cotwist is an autoequivalence. And it turns out that we can write FR as a shift of the functor C composed with FL. So if you remember, these are the two assumptions, the autoequivalence and this sort of natural isomorphism here. They're the two assumptions that we needed in Addington's theorem to conclude that the functor, the twist around F is an equivalence. So as a corollary, the twist around F is an equivalence. Which is what we wanted to prove. And what I want to talk a little bit about next is an example of how we can use this to construct new derived equivalences. So, or actually, sorry, before that. Okay. So this theorem here, it's sort of relying on this assumption, on this X vanishing assumption here, which doesn't seem very intuitive, but we can, if we, in certain settings, we can make it, we can simplify it, basically. So if we know that the dimension of our ring R is 3, and if we know that B is a quotient of A by an idempotent, then the X vanishing assumption is automatically satisfied. So this curly functor T is an equivalence. And this is especially interesting to us because we can get a lot of interesting examples in geometry within this setting. Okay, so now we can talk about the example. So in this example, let's say epsilon 3 is a primitive third root of unity. And let's say that we have a group G, which is a finite subgroup of SL3, generated by the element G, which is a matrix that has epsilon 3 along the diagonals and 0 everywhere else. Okay. Then in this case, G is the cyclic group of order 3. And we can define an action of G on a polynomial ring R, which equals, which is the power series ring in 3 variables. And the way that we're going to define this action is by saying that G acts on a polynomial in x, y, z by sending it to the same polynomial but evaluated at the variables multiplied by this primitive third root of unity. Okay. So we've got a finite group in SL3. We've got an action of G in this ring R, and that means that we can construct the skew group algebra. Which I'm going to denote as G hash R. Wait. Or sorry, R hash G. Okay. And it turns out that this algebra R hash G is a Gorenstein order. And this is due to Auslander. It also turns out that R hash G can be presented in the following way. So we're going to present it as a path algebra of a quiver. And the quiver is going to be a quiver with 3 vertices and 3 arrows between each vertex, like so. And we'll call the outer arrows, so we'll call them x0, y0, and z0, and then x1, y1, z1, and x2, y2, z2. Okay. So the skew group algebra can be presented as the path algebra of this quiver subject to some relations. And the relations are going to look something like this. Okay. So for each I equal to 0, 1, and 2, the relations look like this. And intuitively, this kind of means that the variables x, y, and z commute. Okay. So the skew group algebra looks like this, and what we can do is we can look at the quotient algebra of this algebra by each of the vertex idempotents. So we can let BI be this quotient algebra of the skew group algebra by the idempotent EI. Then this algebra looks like the path algebra of a quiver with 2 vertices and 3 arrows, so it looks like the path algebra of the 3 Kronecker quiver. And this path algebra has finite global dimension. Okay, so basically we're in the situation where of this corollary here that we talked about, corollary 3.3, where we have an underlying Noetherian local Gorenstein ring, which is, in this example, is the power series rings in 3 variables, which has curl dimension 3. And we have these algebras, these quotients of our algebra by idempotents, which satisfy all of the assumptions in the setup. So we can apply this corollary to get some autoequivalences. So the ring surjections we'll call them PI from R hash G to BI. They all induce autoequivalences, which we can call TI, given by R hom over the skew group algebra. of the ideal generated by each of the idempotents. Okay. Yeah, so that's the example I wanted to talk about. And next I wanted to talk a little bit about the Frobenius exact setting. So in this setting, let's talk a little bit about the ambient category that we will work in. So to start off, we're going to place the same geometric assumptions that we placed before. So we've got a ring R, which is a Noetherian local Gorenstein ring. And then we're going to let E be an R-linear Frobenius exact category. With an object P such that add of P is all of the projectives in E. So just as a quick note, under these assumptions, the stable category E is triangulated, and it has a suspension functor, which we'll denote as sigma. Okay. So yeah, so we have this category E, and we're going to assume, finally, the last assumption that we place on it is that the stable category is Krill-Schmidt. Which means that I want all of the objects in E to admit a decomposition as finite direct sums of indecomposable objects. Okay, so these are the assumptions we place on our category, and our setup is the following. So we choose an object X in E, and we'll write A as the endomorphism algebra in E of X, and we'll let B be the stable endomorphism algebra of E in X. Okay, so again, this B is a quotient of A by the ideal proj E, which consists of maps X to X, which factor through a projective in E. Okay. So this is our setup. And we can talk a little bit about the results now. So the first result is a little lemma that characterizes when that two conditions are equivalent. So let's say we fix an integer t, which is bounded by 2, and the dimension of R, which we'll call D. Then the following are equivalent. So first of all, the first is we assume two things. So we assume that if we take the add of X in E, we would like that to be the same as the add of the suspension functor applied to X t minus 1 times in E. And we also assume that if we look at the X groups in the stable category of X and itself, then we'd like these X groups to vanish for all degrees between 0 and t minus 1. Okay. And so that's our first set of assumptions, and the theorem is stating that these set of assumptions is equivalent to the next set, where we assume that the projective dimension over A of B is finite, and we assume that when we look at the X groups over A of B with itself, then we'd like that to vanish. Oh wait, sorry, not with itself. With some simple module S, then we'd like that to vanish for all degrees different than 0 and D, and for all simple B modules S. Okay, so in this setting, I like to think of this assumption here as our smoothness assumption. And I like to think of this assumption here as our spherical assumption. So this lemma states that the set of assumptions in 1 is equivalent to the set of assumptions in 2. And we're going to say that if these conditions are satisfied, then the algebra B is T relatively spherical. So if the assumptions in 5.2 are satisfied, then we say that B and X are T relatively spherical. And here's sort of a quick note. If our algebra B is finite dimensional over C, then 3 relatively spherical is equivalent to being self-injective. Okay. So now we're ready to state our main theorem in this section, which is theorem 5.3, which tells us that if B is T relatively spherical, then the functor T is a composition of tilting equivalences. And so it's also an equivalence. And then we also get a second consequence is that we can compute the cotwist around F. The restriction of scalars functor. And this is just going to be given by the Arham over B of a certain module, which I'll just write here. So it's the module given by the Hams between X and the suspension functor applied to X T minus 1 times, seen as a B module. Okay. So this B module here we can check that actually if we look at add of this B module in B, then it's the same thing as add of B. And this is because B is the Helms yeah. So this is also, sorry, this should be stable Helms. This is the stable Helm. And this is because B is the stable Helm of X, and we know that add of X is the same as add of the suspension functor applied to x t minus 1 times. Okay, so what this tells us is that by Marita theory, C is also an equivalence. Okay. And then just to finish off the talk, I'd like to sort of apply this theorem that we just this theorem here that we just saw, which tells us that if it loads, okay, yeah. Which tells us that if our algebra B is T relatively spherical, then this functor T is an equivalence. So if we come back to our motivating example here, then what we can do is we can take our category E to be the category of Cohen-Macaulay modules over the ring S. Our object X is this module M, and so we know that B is T relatively spherical, is 3 relatively spherical. If and only if it's self-injective. But we computed what B was, right? So we computed that B was isomorphic to C, so B is self-injective. Okay, so now we have that B is 3 relatively spherical, and we can apply this theorem that I just introduced to sort of recover this result of Donovan and Weems that in this setting, this functor T here that we talked about is an equivalence. Okay, so that's what I wanted to talk about. Thank you for listening.
Thank you, Marina. Let's all give the speaker a round of applause. Okay, any questions? Yeah? Just once. Hi, any questions? So I have a couple of very small questions. So at the start, you made a comment at one point that this is where the DG enhancement assumption comes in. But I mean, is that the only place where it probably isn't the only place where the DG enhancement?
Yeah, I mean, essentially, yes, because, sorry, let me see if I can find this definition.
Was this epsilon R? Is it an epsilon?
Oh, it's right here. Yeah. So basically, yeah, because if we want to define the twist, we have to talk about cones of functors. And so to be able to do this in a well-defined way, we need to move to the enhancements. And that's really the only thing that we need to know is that with the functors that we're working with here, it makes sense to take cones, and cone will be sort of uniquely defined up to functorial isomorphism.
I mean, if exactly that were the hypothesis, would that be fine?
Yeah.
And could that not be technically weaker than assuming there is a DG enhancement?
Possibly. But this is like a very subtle point of
Yeah, yeah, yeah.
but so like because I'm only ever working with like tensors of bimodules and things, all of this is okay, right? Like
Yeah, yeah, yeah. Any other questions? Anybody?
So I want to ask, so I think it was theorem 3.1, where you mentioned that you get the derived Nakayama functor.
oh yeah.
That was, just to clarify, that was so this essentially shows that you can construct the Serre functor of dB mod A up to a shift as a cotwist, right?
This of dB mod B, yeah.
dB mod B, not dB
Yeah,
mod
yeah. And
A. Okay.
this is actually something that happens a lot. Usually, yeah, I don't know. Maybe because so in a lot of examples that we know how to characterize the twist and cotwist, the cotwist ends up being the Serre functor of the domain category.
Yeah, I just happened to come across a paper last week which has a similar result
Yeah.
by Babakovi. Maybe you know that.
Yeah, yeah, I do know that.
Yeah. Okay. Great. Thanks.
No worries.
Thank you, Lucas. Any other questions? At the very end, when you move, when you state, when your setup is that you have this Frobenius category and you're taking the stable category, and you were making a, like you basically had like a tilting complex. I shouldn't be calling
Yeah,
it.
well, I guess I didn't really state it, but yeah, so I guess I said that what did I say? I said that T ends up being a composition of tilting.
Yes, a composition of tilting equivalence, and it is an autoequivalence therefore. If I wanted to apply this setup to, I don't know, discrete cluster categories, would I get anything interesting, do you know?
Oh,
That's like one class of categories that I can think of that are.
yeah, that's a good question. I haven't really thought about it. I think maybe so so I think one of the key assumptions is this assumption here, which is basically telling you that you have finitely many indecomposable projectives.
Schmidt, yeah.
And I think, yeah, well, not just Kroll-Schmidt, right? So you're assuming that there's some object in your category E, such that if you take add of this P, it gives
Oh, I see.
the projectives. And this assumption is essentially assuming that you have finitely many indecomposable projectives. So like I guess the cluster category that I'm more familiar with is the infinite rank ones, where we have infinitely many indecomposables.
Right.
Wouldn't work, but maybe the finite ones would work.
Right. Okay. Any more questions, anybody? So is all of this in one of your preprints, or
Yeah, so almost. I'm kind of writing up. So all of the Frobenius category stuff is, but this the Gorenstein orders in the paper, I assume that B is self-injective. Let's see. Let me see if I can find it. Yeah. So in the paper, I'm only assuming B is self-injective, and I only recently now found out how to do it with finite global dimension, and I'm sort of writing that up now.
Okay, thank you. Any more questions, anybody? If not, let's thank Marina once again.
Thank you for listening.
Thank you all for coming. We have Martin Galawa next week. Bye-bye.